Episode 5. Title of the radio enabled course is Energy Physics. Unit 2. Energy from Oceans. In this unit, we will discuss about energy from the oceans, energy utilization, energy from tides, basic principle of tidal power, utilization of tidal energy. Introduction. Broadly, the ocean source of energy are ocean thermal energy conversion, that means OTEC, and the tidal energy, wave energy, and fourth form of the energy that emanates from the sun-ocean system stems from the mechanism of surface water evaporation by solar heating, that means hydrological cycle. These energy sources are the result of the absorption by the seas and oceans of solar radiation, which causes like the wind, ocean currents, and the moderate temperature gradients from the water surface downward, especially in tropical water. The oceans and seas constitute some 70% of Earth's surface area, so they represent a rather large storage reservoir of the solar input. The conversion of solar energy stored as heat in the ocean into electrical energy by making use of the temperature difference between the warm surface water and the colder deep water. The facilities proposed for achieving this conversion are commonly referred to as OTEC plants, or sometimes as solar sea power plants SSPP. Since the ocean waters are heated by the sun, they constitute a virtually inexhaustible source of energy. However, unlike direct solar energy, the ocean energy is available constantly and continuously rather than only in the daytime. The operation of the OTEC plant is based on a well-established physical principle. If a heat source is available at higher temperature and a heat sink at a lower temperature, it is possible in principle to utilize the temperature difference in a machine or prime mover that can convert part of the heat taken up from the source into mechanical energy and hence into electrical energy. The residual heat is discharged to the sink at the lower temperature. In the OTEC system, the warm ocean surface water is the heat source and the deep colder water provides the sink. The temperature gradient can be utilized in a heat engine to generator. This is called ocean thermal energy conversion, that means OTEC. OTEC may be considered solar energy once removed. This energy form has very low efficiency and has very high capital cost because the temperature difference is small even in tropics. Tide is periodic rise and fall of the water level of the sea, which are carried by the action of sun and the moon on the water of the earth. Tides are primarily caused by lunar and only secondarily by solar gravitational force acting together with those of the earth and the ocean waters to create tidal flows. The tidal range varies from few centimeters, about 8 to 10 meters in some parts of the world. The potential energy of the tides can be trapped to generate power, but extreme high capital cost. Tidal energy can furnish a significant portion of all such energies which are renewable in nature. It has been estimated that about 1 million kilowatt of tidal power is dissipated by friction and eddies alone. This is slightly less than the economically exploitable power potential of all the rivers of the world. It is only indication of the magnitude of the tidal power available all of it is not economical feasible also. The first attempt to utilize the energy of the ocean was in the form of tidal mill in the 11th century in Great Britain and later in France and Spain. The power in ocean waves has been part of the human experience for thousands of years. However, this history of attempts to exploit this power for human purpose has been extensive. Patents have been used on a variety of devices and many schemes have been described conceptually. Some small-scale prototype devices have been tested. Up to now, no major development program has been carried through in any country. Small devices are available, however, and are in limited use as power supplies for bios and navigational aids. From the engineering development point of view, wave energy development is not nearly as far along as wind and tidal energy. The hydrological cycle results in rainfall, which causes river flows that can be trapped behind dams to even out the variation in the river flows and thus become the source of either low head or high head hydroelectric energy. Hydroelectricity accounts for some 25% of the world's total electricity capacity. Some countries such as Norway, Switzerland and Canada, because of favorable topographics and rainfall, exceed this average. Hydroelectricity used to account for much more than these percentages in the 19th century, but the advent of cheap coal and steam power plants and the lack of additional favorable hydro sites caused a decline in its use. Many small river hydroelectric plants were established. With the coming of the energy crisis of the 1970s, interest was renewed in these small plants to supplement input to power grids. Small-scale hydroelectric facilities can supply in principle significant amount of electricity for irrigation or potable water pumping, lighting or health or educational purpose. The total potential amount of such a resource is very poorly documented but is apt to be large. In this ocean thermal energy conversion, power production from the energies associated with the ocean temperature difference (OTEC), the tides and waves will be discussed. Hydroelectric power is a major topic and needs to separate complete detail to understand power plant technology. Next, we will discuss about ocean thermal electric conversion (OTEC). The ocean thermal energy concept was proposed as early as 1881 by French physicist Jacques d'Arnouville. In this indirect form of solar energy at sea, collection and storage are free. The surface of the water acts as the collector of solar heat while the upper layer of the sea constantly infinite heat storage reservoir. Thus the heat contained in the ocean, which is solar in origin, could be converted into electricity. By utilizing the fact that the temperature difference between warm surface water of the tropical ocean and the colder water in the depth is about 20 to 25 degree Kelvin. Warm surface water could be used to heat some low boiling organic fluid, the vapor of which would run a heat engine. The excited vapor would condense by pumping cold water from deeper region. The amount of energy available for ocean thermal power energy is enormous and is continuously. Solar energy absorption by the water takes place according to Lambert's law of absorption, which states that each layer of equal thickness absorption the same fraction of light that passes through it. Mathematically, di divided by dx equal to ki. I is equal to I naught small e power minus kx, where I naught and I suffix x are the intensities of radiation at the surface x equal to 0 and at a distance x below the surface. K is an extension coefficient, that means absorption coefficient, that has the unit L power minus 1. K has value of 0.05 meter inverse. For very clear freshwater, 0.27 for turbid freshwater and 0.50 meter inverse for very salty water. Thus the intensity decreases exponentially with depth, and depending upon K, almost all of the absorption occurs very close to the surface of depth water because of the heat and mass transfer at the surface itself. The maximum temperature occurs just below the surface. Considering depth water in general, the high temperature are at surface, whereas dead water remains cool. In the tropics, the ocean surface temperature often exceeds 25 degrees Celsius, while 1 kilometer below, the temperature is usually not higher than 10 degrees Celsius. Water density decreases with increasing in temperature, decreasing again below this temperature. The reason, ice floating. Thus there will be no thermal convection current between the warmer lighter water at the top and deep cooler heavier water. Thermal conduction heat transfer between them across the large depths is too low to after this picture, and thus mixing, so the warm water stays at the top and the cool water stays at the bottom. It is said therefore that in water there are two essentially infinite heat reservoirs: a heat source at the surface at about 27 degrees Celsius and a heat sink some 1 kilometer directly below at about 4 degrees Celsius. Both reservoirs are maintained annually by solar incidence. The concept of ocean thermal energy conversion is based on utilization of these temperatures difference in a heat engine to generate power. The surface temperature vary both with latitude and season, both being maximum in water between the two water levels, the most suitable for OTEC system. Several such plants are built in France after World War II, that is the largest of which has been a capacity of 7.5 megawatt. With a 22 degree Kelvin temperature difference between surface and depths such as warmer ocean areas than in North Sea. The Carnot efficiency is around 7%. This is obviously very low and comparable to the expected from a flat plate collector. The process of OTEC requires that the warm surface water and cold water from depth. Although it is possible to find good land sites where OTEC power plants can be located by bringing the warm and cold water onto shore, it is clear that such opportunities will be much limited on a global basis than the ample opportunities for generating substantial amount of OTEC electricity Onshore OTEC power plants will be viable mainly at locations where three requirements are all simultaneously satisfied with satisfactory economics. First one is coastal zone land must be available. Second one is sea flow must descend sufficiently rapidly from the shore based plant location. Third one is the season availability of warm and cold water without modification. OTEC power generation system gives less efficiency as stated above. However, because of the OTEC requirements for power generation and other losses, the achievable net conversion efficiency is only about 2.5%. Carnot efficiency is 7%. This compares a net efficiency of 30 to 40 associated with conventional power plants. Next, we will discuss about open cycle OTEC system. Open cycle refers to the utilization of seawater as the working fluid, wherein sea water is flush evaporated under a partial vacuum. The low pressure steam is passed through a turbine which extracts energy from it, and then the spent vapor is cooled in a condenser. The cycle derives the name open from the fact that the condensate need not be returned to evaporate as in the case of closed cycle. At the new pressure, water which is entering the vapor gets superheated. The warm water which is at 27 degrees Celsius has a saturation pressure of 0.03619 kg per centimeter square. The evaporator pressure is 0.03213, which corresponds to 25 degree saturation temperature. The temporarily superheated water undergoes volume boiling. The evaporator contains a mixture of water and steam of very low quality. The steam is separated from the water as saturated vapor at 3. The remaining water is saturated at 4 and is discharged as brine back to ocean. The stream at 3 has a very low pressure and high specific volume as compared to conventional fossil power plant which has about 160 kg per centimeter square pressure and 0.021 meter cube per kilogram specific volume. The steam expands in a specially designed turbine that can handle such condition to 5. The condenser pressure and temperature at point 5 are of the order of 0.01729 kg per centimeter square and 15 degrees Celsius. A direct contact condenser is used as turbine exhaust steam will be discharged back to the ocean in the open cycle system. In the condenser, the exhaust steam is mixed with cold water from the deep cold water pipe at 6, which results in a near saturated water at 7. This water is allowed to discharge to the ocean. The cooling water from the deep ocean, which is at about 11 degrees Celsius, on reaching the condenser, its temperature rises about 15 degrees Celsius. Due to heat transfer between the progressively warmer outside water and cooling water inside the pipe as it ascends towards the top, it can be seen that very large ocean water mass and volume flow rates are used in open OTEC system, and that the turbine is very low pressure until the receives steam with specific volume more than 20,000 times that in a modern fossil power plant. Thus, the turbine resembles the few last exhaust stages of a conventional turbine and is thus physically large. Because of the need in the open cycle to harness the energy in low pressure steam, extremely large turbines must be utilized. Furthermore, Degasifiers must be used to remove the gases dissolved in the seawater unless one is willing to accept large losses in efficiency. On the other hand, since there are no heat transfer problem in the evaporator, the problem of biofouling control is minimized. The cost of an open cycle system for providing substantial number of megawatts is presently regarded by most OTEC workers as being significantly greater than for closed cycle system. The turbine cost constituted almost half of the cost of power system, but may be amenable to reduction that could result from design innovations. Next we will discuss about the closed or Anderson OTEC cycle. Heat exhauster known as evaporators and condensers are a key ingredient. Since extensive area of material are needed to transfer significant amount of low quality heat of the low temperature difference being exploited. In other words, large volumes of water must be circulated through the OTEC power plant requiring common saturate large heat exchangers. The actual components employed in a OTEC closed cycle system would appear more like hardware illustrate and another closed cycle. The cycle requires a separate working fluid that receives and rejects heat to the source and sink. The operating pressure of such fluid at the boiler and condenser temperature are much higher than those of water, being roughly 10 kg per centimeter square at the boiler, and the specific volumes are much lower, being comparable to those of steam in conventional power plants. Such pressures and specific volumes results in turbines that are much smaller and hence less costly than those that use the low pressure steam of the open cycle. The closed cycle also avoids the problem of the evaporator. It, however, requires the use of very large heat exchangers, that means boiler and condenser, because for an efficiency of about 2%, the amount of heat added and rejected are about 50 times the output of the plant. In addition, the temperature differences in the boiler and condenser must be kept as low as possible to allow for the maximum possible temperature difference across the turbine, which also contributes to the large surfaces of these units. The closed cycle approach was first proposed by Burjot in 1926, but the most recent design was by Anderson and Anderson in the 1960s. The closed cycle is sometimes referred as Anderson cycle. In the cycle, propane was chosen as the working fluid. The temperature difference between warm surface and cold surface was 20 degrees Celsius. The cold surface was at about 600 m deep. Propane is vaporized in the boiler or evaporator at about 10 kg per centimeter square, that means 10 bar, or more exhausted in the condenser at about 5 bar. Instead of usual heavier and more expansive shell and tube heat exchangers, the Anderson OTEC system employs thin plate type heat exchangers, which minimizes the mass and the amount of material, hence cost. The heat exchangers are placed at depth where the static pressure of the water in either heat exchanger roughly equals the pressure of the working fluid. This helps in reducing the thickness of the plates. The fundamental requirement in closed cycle system is to transfer heat effectively, efficiently across the heat exchanger surface constant, the evaporators and condensers, so as achieve a high value overall heat transfer coefficient measured in watts per Kelvin per square meter. For the evaporation, this overall heat transfer coefficient is measure of how effectively is heat transferred sequentially from a sea water through the heat exchanger materially, that means a metallic ion, and hence to the working fluid, that means ammonia. For the condenser and overall U characterized the reverse heat transfer process. In an ocean environment, it is likely that a layer known as biofouling will eventually accumulate on the water side of the heat exchanger. Such slime is first comprised or microorganism, at which stage the biofouling is called microfouling. Subsequently, if the slime is not removed, additional biofouling in the form of microorganism will become attached. The occurrence of microfouling seems to be prerequisite for the attachment of macroorganism. A film corrosion and possibly of calcareous, that means minerals deposits, can also accumulate on the water side, that is rightly meant as even on the working fluid side of the heat transfer surface. The total formulation of biofouling, corrosion and so on is referred to scaling and will inhibit heat transfer through it. The fouling factor is measure of the thermal resistance RF of the film. This thermal resistance is reciprocal of the correspondence heat transfer coefficient of the fouling film. To maintain viable OTEC, heat exchange provisions must be made inhibit the formation of fouling layers and to remove any significant fouling that forms. Removal can be accomplished by periodically cleaning the heat exchanger surface through mechanical and chemical or other means. Although both closed and open cycle turbines system are being explored, it appears that closed cycle system offer the most promise for the near future. Each of the possible working fluid, that means ammonia and propane, has advantages and disadvantages. Ammonia has better operating characteristics than propane and it is much less flammable. On the other hand, ammonia forms a noxious vapor and probably could not be used with copper heater exchanger. Ammonia has been used as the working fluid in successful test of OTEC concept with closed cycle system. In the heat exchangers, the titanium, aluminum, copper, nickel are the most important materials to be used. The special efforts are being made to improve the engineering design of heat exchangers suitable for OTEC use. In addition, the constructional material must have good heat conductivity and be resistant to corrosion and erosion. By rapidly flowing ocean water, among the material being considered, the prime candidate are already we discussed titanium, aluminum, an alloy of copper 90% and nickel and plastic. These are the materials used in OTEC system. Dear student, in this episode we have discussed OTEC system. Thank you very much. We will discuss the another topic in episode 6. Thank you.